Alright, these are the notes for LT2 in our Applying Newton's Laws unit. And the purpose of this target is to take those forces that we now can identify, such as a support force, a tension force, that sort of thing, and construct a free body diagram, and then use that free body diagram to calculate the net force acting on an object. I can see I have a couple things underlined here, and the first one is the free body diagram. You probably are not familiar with that, but it's a representation that we use to figure out how many forces are acting on something. And then this idea of net force. All right, so there's a couple things here. And we're going to get right to it, and we're actually going to start with the definition of net force. All right. A net force is a combination, so we'll just say a combo, of all forces acting on an object. So the combination of all forces that are acting on an object. This idea of net, okay, it's not like a basketball net or anything like that, but maybe one of the easiest ways of thinking about this, you may have heard somebody, maybe somebody at home who gets a paycheck, and there's a couple of types of incomes you'll see on your paycheck. There's what's called a gross pay, G-R-O-S-S, not like a disgusting gross, but then a net pay. And those will be two very different numbers. A gross pay is what you actually make, what your employer pays you either per hour or per year, whatever the situation might be. The net pay is what you actually put in the bank account. It's what you actually make. The net pay takes into account everything. So maybe you have some money going into retirement that automatically gets taken out. You have to pay taxes on some money, so that's all automatically taken out. Maybe you have payments automatically taken out of your paycheck. All these things. So your net pay factors everything in. Gross pay is just here's what you made, but it's not what you're actually going to take home. So net is a combination of everything. So if we want to do something real simple, like remember yesterday we had that, I think it was yesterday, we had the mug of hot chocolate or whatever the case might be. All right, sitting on the table. And we said the two main forces that we're concerned about is the support force, the normal force pushing up, which is F norm, and then the weight of the cup, so F grav or weight, those are interchangeable, being pulled straight down. Okay. What we now do, which is a relief for me because you've seen my drawing skills, not impressive, is we can put all these into a box. We can put this into a free body diagram to show this net force. So when we see net force, you'll see it represented as F net, which makes a lot of sense. And then something that will make less sense, but also we have to get used to it, is the letter E. It's epsilon. That part doesn't matter. The sum of all forces, because that would be the same thing. Combination, the sum of, we're factoring them all in. So if you see that E, that's supposed to be an arrow, speaking of not being able to draw, it means the sum of. Okay, so the sum of all forces. So now what we would do is we look at this, and let's just pretend here that the force of gravity, the weight of this cup is 2 newtons, because gravity is a weight, or I'm sorry, weight is a force, and so it would be in newtons. And therefore, the table must be pushing up with 2 newtons. Those have to be the same magnitude, the same size. Otherwise, the cup's either going to crash through the table or something freaky is going to happen. If the normal force was bigger, that cup is going to go all Harry Potter on us and levitate into the air. Okay, and that's weird, not going to happen. So, if we wanted to calculate the net force here, since they're going opposite ways, we subtract. And we'll do this more in the next target. It'll be 2 newtons, subtract 2 newtons. The net force is 0 newtons. Okay? And that we could also say then the sum of all forces is 0 newtons. All right, so let's take this simple picture and make it even easier and put it into what is called a free body diagram. Free body diagram. All right, what this does, we could get all fancy and say it's a representation, it's a schematic. It's a picture, all right? It's a picture that shows all forces acting on an object. So it lets us draw them out. so that then we can put them into the math equation and figure out what are acting together, what are acting opposite. Next target. I won't get too deep on that one. So all forces acting on an object. So, doesn't matter what you're drawing. Coffee cup, a castle. It doesn't matter what it is. I have no idea where a castle came from right there. But everything is a box. Okay, you can see why those that are artistically challenged, such as myself, really like these. So if we're doing this coffee cup thing, the upward force is the normal force. Upward forces you draw off the top of the box. So that is F norm. Downward forces, you can probably guess, get drawn off the bottom of the box. F grav. Force of gravity. That is the free body diagram of that situation. You draw a box to represent the object, and then you put all the upward forces off the top, downward off the bottom, rightward forces off the right, leftward off the left side. So let's pretend. I know in my house this could happen, and she gets in a whole lot of trouble for it, but my cat Ethel will randomly jump up on my little coffee table. So when I'm having my Saturday sit and sip, while I'm sipping my coffee in my chair, she likes to jump up here. Well, let's say here comes the cat. I can't draw a cat. So here comes the cat, and she's going to push my coffee cup, and the coffee cup is going to have an applied force to the right. Okay, so let's say it's going to trickle off here, crash, and my sit and sip is ruined. All right, so if that were to happen, we would draw something like this. Off of the right side, because that's the way that Ethel knocked my cup off, would be an F-ap. F-ap is an applied force. Okay, an applied force. So this object now we know is no longer at rest. These two cancel out, but something's happening here. Okay, that darn cat pushed the coffee cup to the right, so it's going to move in that direction. Okay, and again, we'll play with that more in the third one, in LT3. Let's just do one more. Perhaps you have a dog, and if you have a big dog, maybe yours is better trained than mine, but Lily pulls way too hard on a leash, especially when she sees a squirrel. All right, so let's say that you are walking. I don't want to draw it out. You are walking a dog, and what happens is squirrel. Now, if you got your little chihuahua on the leash, I bet you can handle it. All right, scoop that thing up. But if you've got I have a Labradoodle that weighs about as much as I do, she's probably going to win this war. I know she wins this war. She does it often. So here we are. Here's the dog. Okay? Remember, dog is in a box. Everything's in a box. It's lovely. Well, let's think about what forces are acting on the dog here. We're going to ignore me. We're just worried about forces on the dog. We have her weight, which we'll say the force of gravity is down. She is not crashing through the sidewalk because a sidewalk will have an equal and opposite support up. Whoops. That's F norm. I'm sorry about that. F norm. Okay, so we have a normal force pushing up. And then, well, we're able to walk. So there's going to be a little bit of friction. We're going to make that a small vector. Arrows are vectors. The force, the F frict for friction. And here's the problem. Squirrel, right? All of a sudden, Lily puts an applied force on me that is really big. Okay, so she is pulling to the right. She's going for the squirrel. I'm going to try to pull back. Okay, I've got friction helping me a little. I can plant. So then I'm going to put an applied force back this way because I'm over here walking the dog. All right, so that would be a free body diagram of a dog that sees a squirrel, is pulling real hard. These two don't even factor in. They just cancel out. And then I'm hoping, is that these two will offset this one. All right, that's the goal. So that's what we use free body diagrams for, to analyze all the forces in a given situation. All right, and so for this target, you just have to be able to analyze what's going on. All right, so which way do the forces act, and to some extent, which way they move, which we will also deal with in LT3. All right, good luck.